As you all know, there are two routes to AI. My first part is about my assessment of where we are now with AI. These two routes are the computer and the brain. The computer has a very powerful argument in its favor. It's a universal machine. Whatever the principle of the brain, if you can couch it in terms of an algorithm, you can run it on a machine. There is no limit to that. That was the thought that riveted people in the field in the 50s, when they founded this field, artificial intelligence. As you know, it arose with the Dartmouth conference in '56. The term goes back to John McCarthy. A problem with that is that the computer as such is completely empty, has no tendency to go anywhere. Everything has to be loaded into it by humans. It's totally dependent on human collaboration. I want to skip this slide. The brain also has a very convincing winning argument. It is a proof of existence. It evidently it shows what can be done. This thought spawned the field of neural networks and its ilk, machine learning and Bayesian estimation and so on. And in its present incarnation, it's called deep learning. And it has, in this version at least, it has a drawback, which is it is totally dependent on annotated data, as you all know. So in a way, the computer has a frame that is much too large, so that classical AI got bogged down by the combinatorial search problem, as you know. There is too much space from which to pick structures. And a main point I'm going to make is that the neural networks approach has a frame that is much too narrow. It cannot possibly contain the answer. It cannot possibly contain the solution to the artificial intelligence problem. And in its present version, neural networks don't capture what is going on in our brain. Okay, so by conclusion, it's a pessimistic view, or maybe a sobering view, but I think we should face it. AI today is totally dependent on human thought in a detailed way, either by needing programming or by needing annotated data. So I once wrote in one of my blogs, it is nothing but human thought in tin cans. A little overstated maybe, but worth thinking about, I think. An important point here is in a detailed way. It is a matter of grade. Of course, you can run a computer, run a system today in a much more powerful way than was possible 20 years ago. So there is a gradient going on, and that is the gradient of my second topic, gradient of scope. When you have a system, it has to deal with a wide range of scopes. And, you know, I'm old enough to have lived a period when a decent PhD thesis in computer vision was about analyzing one single image, one single picture. And the usual truth of the matter was the next picture wouldn't work. So that was very limited. We are much further now. We now have systems that I'm referring to the second. No, this is not what I wanted. How can I switch on the... Oh, here. I'm now referring to the second cone here. We are much further along. We have systems that can deal with a whole benchmark, with a whole series of pictures in that particular case. But we will have to go much further in order to increase the contextual scope of our systems. how can you increase the scope of systems? I think there are two rather obvious points. You have to decompose the situation with which the system is to deal into aspects. Envision that would be, for instance, texture, form, motion, depth, illumination, gist, you know, the type of scene you are handling with, and of course the agenda under which you want to analyze the images. Decompose into aspects, and these aspects have to be relatively abstract. So they have to be abstract relative to each other. One has to abstract from all the others, as far as that is. Better now? Okay. Relative abstract, and the word relative also refers to the fact that they cannot be totally independent of each other. Relative aspects. So, for instance, when you are about object recognition, you want to be translation invariant. The recognition or the representation of objects needs to be totally oblivious of where the object is in an image, in a principled way. I think these 2 points are pretty obvious. And I think what is necessary is that the level of abstractness is to be lifted much higher in order to reach much larger contextual scopes. Now, I would like to remind you of the fact that children or animals, when they come into the world, are born with a repertoire of behavioral patterns, of instincts. And the miracle, if you want to see it that way, is that they can apply them immediately in a natural environment. A gnu that is being born can behave in the savannah minutes after birth. So the level of abstraction of the drives that are built into animals is very high, and there is a mechanism to link them, these drives with concrete situations. That must be our goal. We want, of course, to be able as humans to formulate on this level here, want to formulate goals, agenda, purposes, and want the system to be able to adapt those purposes in no matter what context. That's the goal. Now, there is a very fundamental point of creed here, and maybe I should take a vote with you, is generic artificial intelligence a matter of sweat? Will it take decades of hard work, as it has in the past, or will there be the possibility of a sudden breakthrough? Who is for sweat? Interesting. Who is for breakthrough? Oh, great. Okay, I didn't expect that. I am an adherent of the El Dorado hypothesis that there is indeed a place to be found where the solution of this grand problem can be found in a matter of a breakthrough. And I have two arguments. One is, remember that we bring up our kids in very simple and very stable nurseries. They are expressly made simple and stable, and in a matter of 2 or 3 years, infants are able to grasp the reality of their immediate environment perfectly. We forget that we speak about the reality with the baby, with the kid not thinking about particular features that need to be paid attention to. We take it as a given that they see the reality, that they think in terms of the reality of their environment. At about 3 years of age, they begin to speak, and they can exert their will. If you have young kids, you know what I'm talking about. They have a will, and they can interact with the world in terms of their will even before the second year of their life. when you show them at the age of 3, they need to learn about the world for about 3 years. If you show them a new implement, like a tricycle, they inspect it and know them all of them. There's a great variety of possible tricycles in the world, changing in shape and in exact color and so on and so on. But they get it, this is a vehicle, you can sit on it, you can steer it, you can drive it. They know what a tricycle is. One-shot learning, that's what they have. My other argument is a very powerful tool, I think. If you want to describe the wiring pattern of the cerebral cortex, it takes you a petabyte. It's a very easy calculation. A petabyte of information. But what goes into the making of the cortex? You have 1 gigabyte of genetic information, or probably much less. This is an overestimate. And I claim it will be possible, in principle, to to create a training environment by virtual reality on the basis of 1 gigabyte. That's about the size of computer graphic systems today. And speaking of the size of the program that you download. So that's a tremendous gap between 1 gigabyte and 1 terabyte, 6 orders of magnitude. So 99.9999% of the structure of the brain is not explainable on the basis, direct explainable on the basis of these. There is no mystery, of course. You all know of Kolmogorov complexity. The information content of something, in this case the cortex, is given by the shortest algorithm by which you can create that structure. But the good news here, the El Dorado news, if you want to see it that way, is that the brain is obviously totally dominated by regularity. It's totally dominated by regularity. You don't need to train each synapse in the brain by statistical input. The brain has a very powerful prejudice about in what states to fall, and this prejudice is evidently tightly tuned to the world in which we live. That's a very important point. Okay, there is an El Dorado. We will be able to create electronic organisms with human level intelligence. We only have to find the El Dorado. Where is it? Where do we have to look? Here is my essential point. I think I know where to look, and it is about the neural code issue. When you look at any scene like this here, or the scene you are surrounded by, when you open your eyes, it takes 1/10 of a second for your brain to create a model of that scene, to construct that scene. What you are seeing is, of course, a construction in your brain in this moment. You get visual input, you get tactile input, and so on, but a very large part of the information contained in your scene representation comes from inside. In this scene, for instance, in the picture is nothing about depth, there's nothing about materials, about the significance of patterns, the affordances, the opportunities to act, and so on. All of that comes from inside. That is a construction. And the important question that is raised by that is, how do the nerve cells in your brain manage to create this mental theater? It's not only vision, as you know, it's audition, it's emotions, it's pain and drives and all of this. It's all expressed by neurons. That's what we all believe, I think. How do they do that? That is the neural code issue. How do they generate the phenomenon of your mind? And I will give you my answer to that, and I hope I will be able to convince you. This picture here refers to a face recognition system which I once built with the express intention to convince my colleagues that my way of thinking of the neural code issue is the correct way. It was a complete failure. My colleagues don't believe it, still don't believe it, but it was a good basis for two companies, one in Los Angeles, one here in Germany. They are still alive in their own way. So the idea about face recognition is this. We know that if, a picture of an object or of a face enters our brain as a two-dimensional, in primary visual cortex, as a two-dimensional array of local feature detectors. That is on very solid experimental basis. We know that primary visual cortex, which is called aria striata, for a very good reason, because it is dominated by lateral connections. We know that these feature detectors are laterally connected as a two-dimensional sheet with rather local connections. So that is the representation of the face when it comes in. I claim in order to recognize it, you need a model of that face in another part of the brain, that would be in your fusiform complex, in your inferotemporal cortex. You need a model which is homeomorphic, meaning that it has, to some approximation, the same feature detectors as in the primary visual cortex, arranged in the same two-dimensional array. And the mechanism to link the two is another network pattern, which are these projection fibers here. And the point at which I'm diverting from everybody else in my field, in neuroscience, is that I believe that those connectivity patterns can switch as quickly as you move your eyes. So when you move your eye, then the image in primary visual cortex moves, of course, and you will have to build up a new set of those projection fibers. Now, the point I want to make is, these are three, what I call network fragments. This is one, and those connection fibers are another network fragment. And the point I'm making is that our brain is totally dominated by such network fragments, which are built in a slow process. I'm going to comment on in the next slide. Are built in a slow process, which can be switched on and off as quickly as you think. They are the Lego blocks of your mind. That is the language spoken by the brain. Now we have three such network fragments here. They cannot be combined in arbitrary fashion. There is a very, as I said earlier, a very potent structural principle dominating the structure of these. And that principle is that each individual connection, like, for instance, this one here, from here to here, is embedded in alternate pathways, which help it to create correlations of signals between here and here. An individual connection is only good if it has partners, cooperative partners that link up the same places. And these connectivity patterns are all constructed of lots of such meshes. For instance, the link from here to here gets help from the link from here to here, the alternate pathway. And these projection patterns are a dense mesh of such cooperative loops. That's the idea. And let me make another very important point. I think this is a point that is necessary to open the door to true intelligence in the machine. The decision that is happening here, that this is the correct model for this face here, is not taken, not necessarily taken, is not taken by an individual neuron that says, I know this guy. There was the marvelous period when he was our president, for instance. In this case, the decision is taken by the establishment of this whole network. The decision is a collective decision. And a particular network may never have been created in the past, but it falls together out of pieces, out of structured network fragments that have been built in the past. Now, a word about these self-organization. If you have a set of active neurons, then symbolized here, then it creates spontaneous signals if you give it enough time. And these signals act back by synaptic plasticity, by this correlation statistics on the network. This usually would be a runaway situation. The network is changed and changed and changed, but there are certain networks that are stabilized by this loop. And those are the important networks I'm talking about, the network fragments. I have the word net for them. Now, in order to do vision, which is my application domain, it suffices to have two types of such network fragments, very simple types. One is two-dimensional neural fields with local connectivity, as I had employed for the face of Obama. And the other type is neighborhood-preserving projection patterns between them. And with that, you can do vision. That's what I claim. Let's analyze a particular process when the child, for instance, looks at the implement tricycle. I would like to refer to an idea which was very important in good old-fashioned AI, GoFi, if you have heard the name, which was trampled over by neural networks in the early 80s. You know, people like Marvin Minsky or Roger Schenck, they talked of frames or scripts. The idea is that you understand a scene, or in this case, an object, by relating it to a frame, to an abstract frame. Remember, we are talking about a deep abstraction which is necessary. You link it to an abstract frame which has the same parts in the same order, in the same connectivity pattern. These connectivities here stand symbolically, in reality it's much more complicated, for the spatial relationships in the intrinsic coordinates of the object, which has a front and a back, a right part and a left part, although this is left to that in the picture. And this frame is represented by a net which is composed of subnets, which are either recognition structures for parts of the object, which you have to have learned before you have spent 3 years on that. You don't have these part descriptors, and you have these coordinate fragments inside your model, and the two your model, and the two are linked by a set of connections, which, for instance, do the transformation that you need to do if you walk around the tricycle. Then they change their structure. You need to implement the proper control of these network patterns. That's what I find is the essence of intelligence. And in order to convince you of that, I'm going to throw you into a test. This is the Raven matrix, which is part of the intelligence test. And in order to perform on this, you first recognize, of course, we are in an exam here. You are in an exam here just now. You have to solve a problem. What is the problem? Well, there's a question mark here. And there is something like a menu. This you recognize as a matrix. And as you probably know, the problem to be solved is you have to find some kind of schema that unites the figures in rows and columns and establishes a relationship. And what you have to do is to fill this empty box here with one of the menu items, such that those relationships are also filled true in the last row and the last column. Now, is there any answer? What is the letter? Well, I sent you to sleep. I can see that. You are all very intelligent people. Well, what you have to discover here is there is something to be counted here, those points here. And if you have numbers, you can apply arithmetics. So 2 plus 1 is 3. 3 minus 4 is minus 1. And 5 minus 3 is 2. Okay, that's... I just wanted to give another argument that, in our view, intelligence means interpreting the environment in terms of abstract schemas, very abstract schemas, like number here and matrix and menu and so on. Now, this is my last slides. I'm just being sent a message. Please finish your talk. What I am planning to do in my company is solve the vision problem, which is hanging, the computer vision problem is hanging due to the fact that there are lots of very intelligent algorithms to solve individual problems, individual aspects like motion detection, depth texture and so on, but they don't work together. The problem of vision is that when you start with a picture here in the middle, you have to project it into those different aspects, but these projections at first are totally ambiguous. You cannot possibly know what the depth is unless you also know about the other aspects. So the way that is solved is you need an architecture in which those different aspects talk the same language. And guess what that language is? It's of course net fragments. And they are connected on the basis of experience by complex net patterns that have stored, as a matter of experience, combinations of values that together with the image make sense. So that this cloud of, ambiguous cloud of responses to the image collapses into something that forms a well-structured network. That's what I see as the vision problem. And if I have at least intrigued you, please contact me, write me an email, I send you information. Please disregard those two letters, which I don't know how they ended up here. Thank you.